Thank you for that introduction. Okay, the topic is quantum cryptography. Now, what I'm going to talk about is a marriage of mathematics, physics, and computers. And now, I have a challenge in front of me. This is mathematics. Well, Dr. Ramarao just talked about the latest development in the latest field. I'm going to talk about something that was done by an ancient mathematician by name Euler. But the beauty of it is that mathematical result that Euler did with absolutely no idea of how it is ever going to be used in any context is something, it was a beautiful result. That result has been used today in cryptography, which finds applications in information security. Euler never dreamt of it. He had no idea what a computer was. To him, a computer was all up on his head. That was all the computer he knew. But today we are finding use of that. The second part of the marriage is physics. People who develop quantum physics did not ever imagine that it is one day going to be used in this context. A use for quantum physics was never their dream. Their dream was to understand nature, the beauty of nature, the kind of challenges nature poses in understanding it. These were the things that motivated physicists to develop quantum mechanics. Quantum mechanics came out of necessity of contradictions that were observed in the nature, in the way we believed we understood nature, and we were trying to go around. There was a famous statement that was made. All that can be done in physics has been done. This was a statement in the early 20th century that people used to make. All we have to do now is to measure physical constants to a greater accuracy, and that's it. But then, when they started doing these things, they started realizing that there were many contradictory things that they couldn't explain. So the birth of quantum mechanics, special relativity, all these things happened because of that, not because they thought one day it will be used in quantum cryptography. The third part of it is computers. Computers were developed for use of humanity. People, of course, mostly computers were developed with a commercial angle also in mind. People like, and today, IBMs and HPs and Googles of the world are the richest companies. And they took all of these, not these companies, but computer scientists developed an entire field and started applying these results that were developed long time back with no intention of actually applying these results in this context. But these results were actually useful, actually applicable in present world. And that is the kind of thing that I'm talking about. And the other challenge, as Dr. Ramarao pointed out, there was a speaker who spoke on superconductivity, and without an equation, without mathematics. And today I'm going to try and do the same. I'm going to talk about mathematics, I'm going to talk about physics, all of which will need equations, but I'm going to do without equations. And in reality, it is the beauty of nature. It's just the thirst to explore that beauty of nature is all that we need. And if today I'm successful in communicating to the young generation that beauty is what you should seek, I will be successful. And in the process, of course, you will hear a little bit about quantum physics, you will hear a little bit about light, photons, you will hear a little bit of mathematics. All of these and how beautifully they all come together is the exciting part. So I hope I convey that excitement that I have in me when I learn these things, when I go through these things. I hope part of it at least will get into. So let me start. Oops. So what is the purpose of cryptography? It is to provide security in internet communication, storage of data, which is a very practical application. Today the world is digitally connected. without a digital device, we are pretty much in dark ages and we really will not know how to live. However, what happens is when a technology is developed, typically people develop the technology for a good purpose. They want progress in humanity, they want ease of life, a good standard of living. So technology is developed. But in the process, there are also lurking behind the elements are unscrupulous people who want to misuse this technology and gain unfair advantage, gain illegal advantage. And this is what has happened in computer also. We all know that. Today, as a matter of fact, if you connect a computer system to the internet, and if the system is unprotected, within minutes, I can guarantee you that your system will be attacked and you will lose all the data. Now, at worst, it can damage a lot of things. It can end up resulting in a lot of loss for you. At best, it might be a nuisance. You might have to reinstall the operating system and you might have to start afresh again. But now I have to master this. So here is a very high-level table of contents for what I'm going to say during the hour. I'll start with what is information security, mainly because I need to set the context. We need to understand what problem we are solving. And unless I do that, it will be just a talk and with no context, and it will be just hanging in the air and we all go home without really without understanding what I was trying to say. So I'll set the context, and that context also leads me to talk a little bit about what is cryptography, what actually do we mean by cryptography. And then I'll talk a little bit about what are the challenges that are faced in classical cryptography. I'm calling it classical cryptography. That terminology isn't standard. Nobody calls it classical cryptography because the cryptography that is being used is classical. The reason quantum computers, quantum cryptography, all these things are today only a laboratory piece. There isn't a real quantum computer that you can go and buy in the market today. Okay, so that's something we need to understand. Then I talk a little bit about quantum properties because that is when once we understand the challenges and what challenges we are going to actually try and solve, I will then go on to say what are the properties of quantum mechanics that are relevant for this. And then I'll talk about quantum cryptography. And in this I must start by telling you that what I'm going to do is only touching the tip of the iceberg. There's a lot more than what I'm going to say today. And not only a lot more, but you will probably just kind of skim the surface and hear the terms and get to know what there is. And because I'm assuming that the audience does not have a background in cryptography, does not have a background in quantum mechanics. So marrying the two when neither of them is in existence is going to be the challenge. Let's see how well I succeed. So, what is it that we're trying to do when we say information security? There are three things that are essential for a computer system. You have data that you need to protect. You cannot let anybody get access to the data because some of this data are critical. It could be, and to talk practical terms, it could be your credit card information. It could be information that people can misuse and cause damage to you. So we need to have that confidentiality. We need to be able to make sure that only I can access the data that I store and only others who I authorize can access the data and nobody else. That is confidentiality. Integrity is, and by the way, this also refers to not just information that is stored on the computer, but when you are dealing with a transaction, when your data is going on the wire or wirelessly to some other recipient, such as, let's say you're doing a bank transaction and you're saying, I transfer 1,000 rupees to Sateesh. If in the middle I go and say, I change the 1,000 to 10,000, how would it be? And that precisely can happen. So, we need, when I say confidentiality and integrity, it refers to data that's not only stored on the computer but also in transit. I need to be able to make sure that the data that I send is the data that is received by the encrypted recipient. That is the second part of information security. The third part is availability. A system that is meant for me to use should be available at the time I want to use it. If a bank server, if you go to a bank and there is no guarantee that the bank is open or closed and they will open at their will, how would it be? And you want the bank to be open when they say they are open. And when a computer system says they are available all the time, you want the bank to be, the computer system to be available all the time. Availability is something that one should take for granted. You need not have to worry about the system that's being available. This is a very complex matter. Not only related to information security, but also in general, the ability to guarantee that a system runs without stopping. Now imagine, as a matter of fact, I should give you an example here. Due to a security glitch, the New York Stock Exchange shut down for just 1 minute. And during that 1 minute, on the order of about $10 billion was the loss incurred. Now, talking in those terms, you understand that it is actually a loss, but a lot more can happen. There are mission critical systems. I'm pretty sure you are all aware that all our aeroplanes and the entire avionics industry runs on electronics. They all run on so-called mission critical systems. If it malfunctions, even for a second, the entire plane can go wrong, causing untold damage to lives. Now such things ought to be avoided. That is a part of security. And enabling seamless communication between parties involved. If I'm talking to the bank, it's I and the bank that should be talking. Nobody else should be able to intervene in the middle, nor should they prevent me from talking. This should be the thing that we should take for granted. That is the purpose of information security. Now, how does one make it possible? How can one have information security? One of the critical aspects of information security is the cryptographic aspect. It's a highly mathematical subject, as we will come to know soon. Cryptography is divided primarily into two parts. One is called cryptology, and the other is cryptanalysis. Cryptology is applying mathematical techniques or applying other techniques to make sure that the data is secured, while cryptanalysis is the art of actually breaking ciphertext without the knowledge of other things that you need to know. That term secret key, we will come to know what it is soon. Now I should tell you a story here. During the Second World War, Germany, we all know, lost the war. One of the reasons attributed for the loss is actually cryptography. What had happened was they had a machine called Enigma. And Enigma was a machine that was used to encrypt information or any communication that was going from the headquarters of the army to the soldiers on the field. Now, they assumed that nobody can break this cipher, that any transmission of this information will only be received by the soldiers on the field and execute the orders as per the information set. Now, unknown to the Germans, what the Allies had done was actually break the Enigma system. When I had broken that system, they knew exactly what was going on. So they would capture this message that was being transmitted. They would change the message in the middle and retransmit that as if it was coming from the headquarters. So the German army soldiers were completely misled. They ended up executing the wrong orders, and in the end, because of that, they lost the war. Is one of the stories. Now, such a thing falls under cryptanalysis. There was a whole team of people, largely mathematicians, who sat together and understood how this enigma was working. They deciphered the whole thing and used it. But today, cryptanalysis is definitely not a part of what I'm going to talk about. Coming to cryptography in the sense of cryptology, now I'll mostly be using cryptography even when I mean cryptology. So when I say cryptography, you should understand I'm talking about only the left-hand part of this picture. There are two types of cryptographic techniques. One is called symmetric key cryptography. The other is called public key cryptography. Now, what is symmetric key? As the word itself says, there is something that is symmetric, same as, and if two parties are involved, there is something that is the same. And that same is the fact that between you and your correspondent, you have a shared secret. In fact, I should also tell you that cryptography is not something new. Once again, we go back to very old things that have resurfaced in a different context. Cryptography has been known to have been used by Caesar. In fact, one of the techniques is called Caesar encryption. Caesar key. Caesar would encrypt the data by just, it was very naive. All he did was shift the letters by a certain amount. So if you shifted A by 3, it would become D. So T by 3, D, E, F, G D would become G. So each letter was substituted. It's called Caesar substitution sign. So that way, at the first glance, unless you know that there was this shifting of the letters done by a factor of 3, you won't know what the message was. It was that simple, but there are more sophisticated things we do now. So the symmetric key refers to the fact that when you receive the message, what you do is shift the letters back by exactly the same amount as was shifted in the first place to encrypt. That is why symmetric. So the shared secret allows you to do the exact same operation as was done by encryption, or the reverse operation also requires the same secret as was used for encryption. That's why it's called symmetric key. Public key, on the other hand, is a different beast. That involves very interesting mathematical concepts which we'll come to, where the key that you use for encryption, that is hiding the message, is different from the key that you use for decrypting the message. So the two are not the same. And this opens up a large number of possibilities, some of which we will talk about. So going to here, this is pretty much exactly what I have been saying so far, that encryption key is the same as the decryption key, is symmetric cryptography. Public key encryption is characterized by using two different keys. That is, one for encryption and one for decryption. How do we do it? What exactly is the method that is used? There are, as I was saying in the beginning, some beautiful mathematical results which come in handy. There are functions in mathematics called one-way functions or trapdoor functions. These are functions which either you need to know something that helps you perform an operation, or the operation is easy to do one way, but inverting it is extremely difficult. I'll give you an example. If you take prime numbers, just multiplying two prime numbers is an easy thing. Anyone can do it. I'm sure everyone can do it. If you are given two large primes, now by large I mean prime numbers of the order of let's say 200 digits, 300 digits. If you're given two prime numbers, even such large prime numbers, multiplying them together is not a difficult task, given that you have powerful enough computers. In fact, any of the laptops can easily do it with appropriate programming. But if I give you a large number and ask you to, large number typically means let's say 400 digits, 500 digits, and ask you to factor that number back into its prime components. That, believe it or not, is a problem that nobody has solved. It's not easy. With huge number of computers that are available, people still can't do it. I'll be talking a little bit more about this, so here is how things happen in a communication. So we will from now on speak to communication. Storage is not our problem because quantum computing is, or quantum cryptography is today typically applicable in the context of communications. So using the symmetric key, here is what happens. You take the plain text, perform the operation now. Perform some complex operation. Now, I'm not going into the details of this complex operation because that will involve writing equations which I'm not going to do. You take the plain text. Now, mind you, plain text in this context is still numbers. Everything in computer is encoded in binary. The binary system is nothing, there is nothing sacred about binary system. Any number that you have in your base 10 system can be written in a binary system. So everything is numbers. We're just talking about numbers. So you take that plain text which corresponds to a certain number, make an operation using that encryption key, which becomes a ciphertext. Now, unless you have the same key available to you, you will not be able to understand anything from that ciphertext. Now, typically, this is the way things happen. You're sending something, there is somebody in the middle trying to capture all the data and then trying to see what you're sending. If you've not encrypted the data, people will capture the data and then do all kinds of things that you don't want done. So, if an information is encrypted, such a thing is not possible. Now, at the recipient end, the recipient gets the ciphertext, and we are assuming that there is a shared secret. The shared secret is the encryption and the decryption key, which are the same in the case of symmetric keys. Then the recipient uses the decryption key to perform the operation to get back the data that was sent. So now you have the original data available. So this is the mechanism that is deployed in symmetric key encryption. Now the problem is the following. I have to share a secret. How am I going to share a secret? Of course, one way is I can send somebody with a disk or with a pen drive with the data. But what is the guarantee it will reach the person I want it to give it to? The person may not be trusted. the third person that you're sending. Or you can go yourself. If you go yourself, you don't have to have any of this. You can talk the secret yourself. So the problem here is one of how do we actually share it, or share the secret that the two of us should have. That is one of the problems. You keep in mind that there is that problem. So this I talked a little bit already. It's easy to compute one way, a function like the multiplication of two large prime numbers. Or there is another example which is called discrete logarithm, which means if you, sorry, this is an equation, but it's not just an equation. I don't think that really should count as something to deter you from listening to the talk. So discrete logarithm is again just dealing with number theoretic results. Just like you have logarithm that you, I don't know, these days people use logarithms to calculate. In our days we used to use a log table, plots table, and look up the logarithm and then the multiplication and all that used to be done using that. Today I guess you just punching a number into calculator and then do it. And so in the context of modular arithmetic, which is again not a very sophisticated thing. All of us are very familiar with modular arithmetic. For example, a clock runs 12 hours. After 12 it becomes 1, it doesn't become 13. Except in the military where after 24 it becomes 1. So modular arithmetic is just that. After a certain time, the number goes back to that. It's only those finite elements. It's only 1, 2, 3 up to 12 that forms the entire arithmetic. So in such a case, discrete logarithm is a logarithm, x is called a discrete logarithm. If you, of b with respect to a, if you have to raise a to the power of x to get b. This is exactly how logarithm is defined in our case also. Let's not worry too much about it. Just the point that given a and x, it's very easy to compute b. But if you're given b and a, believe it or not, finding x is very difficult. That is the problem of discrete logarithm. All of these are actually deployed in systems that provide cryptographic techniques. In fact, factoring of a given number into its components is the mathematical problem that is used by the so-called RSA encryption mechanism. RSA stands for the names of three people who invented this method. It's called, their names were Rivest, Shamir, and Adelman, and their names is what is used for that. So one of the arrows is missing, but here is how public key mechanism works. Everybody in the world has a lock and a key to actually lock that padlock. You have a padlock which is a padlock for the information that you're sending. So you take the information, you put it in a container, and I'm just now you have to imagine all these things. This is not a physical container. This is not a physical padlock, but everybody in the world has that thing, meaning that information is accessible by anyone. You can take that lock, you can take the key, take the information, put the information in the container, lock it. But once you lock it, you cannot open it anymore. That is the condition. So what you do in public key encryption is just that. Take that information, put it in a container, lock it, and send it on to the recipient. Now, it's only the recipient who has a separate key that can unlock this locked padlock. So the recipient, then what you're doing effectively is anyone can send a message that is encrypted, but only the recipient can unlock it. So this way, you are able to now share anything that is in confidence. How is this used? You actually encrypt I'll tell you first how it is used and then tell you why it is used only that way. You take the shared secret that you want to share. Remember the symmetric key encryption needed something to share with the person you are communicating. You take that secret, lock it up and send it along. Only the person that you want to share with is the person who will be able to unlock it. So now the two of you have a secret that is shared with you. Of course, any communication you want to do can in fact be done this way, but it's an extremely expensive process. To encrypt a huge amount of data using RSA mechanism takes a lot of time and a lot of resources. That is why what you do is use this mechanism only to share the secret key or share the shared secret, and use the symmetric key mechanism to actually do the data transfer. So, public key mechanism provides us a way of achieving key sharing. You can share the keys between any number of parties by using public key mechanism. And often what happens is somehow, somewhere, somebody might have catched up the key. So you might want to change the key, you might want to do it many times. All these various factors enter into account. And there is also another thing, perfect security using shared secret is possible, but mathematically it can be shown that that is possible only if the length of the key that you are using is the same as the length of the message that you want to send. So if that is the case, it becomes extremely difficult for you to generate the key and share. So this is just another way of showing the same thing, and I'm again continuing to talk about the RSA mechanism and discrete logarithm. And there is also another thing called elliptic curves. All those are names that you need to hear now, but I'm definitely not going into the details. So you take the symmetric key, you create an encrypted key, send it across to the recipient, who is the only one who can open that encrypted portion of the data and read the key. Now the two of you share a secret. What is the problem with this? Well, it works beautifully. By the way, in most of your communications today, whether you know it or not, you are actually using RSA mechanism. When you say HTTPS, it is a mechanism that actually uses RSA mechanism to secure the data during transmission. So you are actually using it whether you know it or not. In 1977, RSA, that is Rivesh, Sharmir and Nadelman, issued a challenge. They said anyone who can break this new kind of cipher that we have developed, we will give you $100,000, but it actually takes at least 1 million years for you to do this. That was their challenge. 1 million years, mind you, that is how confident they were of their system. But the prize was claimed by a group of scientists, actually mathematicians, in the year 1994. Now this highlights the challenge. It's not a perfect system. It's not mathematically, it's not that a one-way function is not invertible. It is invertible. It's only difficult to invert. Now, with enough development in mathematics and in computer technology, it is quite possible that you can break this. As a matter of fact, and this is unfortunately something I'm not going into, it's called Shor's algorithm. Shor's algorithm is developed to precisely do that, factor a large number into its prime components, but the difference between the regular way of doing it and Shor's algorithm is Shor's algorithm uses concepts of quantum computing. Now, using quantum computing, you can substantially reduce the time it needs for you to factor large numbers. So, within minutes, once we have a quantum computer, you can actually break RSA machines. Similarly, other mechanisms that are used, it's just a matter of time before somebody invents a way of doing it that will break the system. So, what I'm trying to drive at is, yes, there are ways of doing it and we are doing it today successfully, but there is no guarantee that it will remain the same. If quantum computers become a reality, for example, many of these methods will not be safe anymore. So we need a way of doing things differently, which does not just depend on the difficulty of doing something, but from first principles, is there a way of doing things that is guaranteed that what we do is perfectly safe? This is the challenge we're going to address. So these are things I've already talked about, so I won't go more into them and go to. Before I get into that, let me, since this is also about light and photons and so on, and the fact that I'm actually going to use some of these concepts, I'm going to talk a little bit about photon polarization. What is polarization? You have, when light transmits, when light is a photon, it goes, and you probably have heard it a million times, so I don't have to go into details. If light is transmitting in, let's say, a Z direction, the electric field that is associated with the light, after all, light is actually the result of oscillations or vibrations of electric field and magnetic fields. Now, the electric fields are always perpendicular to the direction of propagation of light. Now, perpendicular doesn't mean only one direction, because if you look at this plane, any line in this plane is actually perpendicular to the direction of propagation. So there is an infinite number of possibilities. The electric field can be oscillating in any of the directions. The direction of oscillation of the electric field is what is known as polarization. And in the world, there are things called polarizers. In fact, if you wear a Polaroid sunglasses, that actually does that. It's a filter which allows light to transmit only when it is parallel to its axis. That is polarized parallel to its axis. And anything that is perpendicular to its axis is going to ground. So the net result is a reduction in the intensity of the light that goes through the polarizing filter. Now, what happens is when you send an intense beam of light, such as light from the sun, it's polarized in all directions. And it's a random polarization. You have vibrations of the electric field in all directions. But when it passes through the polarizer, its intensity is reduced by a factor of cos squared alpha. Now let's not get into various numbers, various mathematical stuff, but suffice it to say that since only portion of the light is passing through, the ones that are passing will reduce the overall intensity of the transmitted light, and that will be reduced by a factor of cos squared alpha. Now, switching gears from classical to quantum, what are the elements of quantum mechanics that are going to be relevant to us? there is the famous Heisenberg uncertainty principle. What it says is the following. If you have a quantum object, the quantum object cannot at the same time be precisely defined to be in a position or at a position X, and at the same time know its momentum precisely. There is an uncertainty involved. Imagine the following. Whenever you observe something, the act of observation itself is going to cause a disturbance. And when it might not come to you as a surprise, you will probably have learned it in a gold standard. That, as a matter of fact, the gravitational force of the Earth or the Sun on the Earth is what makes Earth go around. But at the same time, the Earth, in fact, exerts a gravitational force of the Sun. But it's such a small amount you won't observe. Similarly, a huge object like us, for example, you're seeing me because photons are falling on my body and is getting reflected, and you're seeing the reflected photons. But those photons are not really disturbing me. You're not visibly seeing me literally because photons are falling on me. However, imagine a photon falling on an electron. That's going to hit the electron. The electron being such a light particle, when the light falls on that electron, the energy of the photon actually disturbs the electron. So there's no way you can observe the position and the momentum of an object which is quantum mechanical at the same time. So that is what Heisenberg uncertainty refers to. I thought I would throw in a qubit at the same time. Heisenberg uncertainty principle leads to quantum mechanical description of the universe or of nature, such that a system of quantum mechanical objects is never in one state. There's a famous story that there's called a thought experiment. It's called the Schrodinger's cat. Schrodinger's cat was the following, where there's a cat inside a cage, it cannot escape. There is a bottle of cyanide, a deadly poison, that gets disturbed if anybody observes it. It can either spill or not spill. If the bottle opens and spills, the cat will be dead. If the bottle doesn't open, the cat will be alive. Now, if an observer is not looking at it, we don't know what the system is doing. Whether the cat is still alive or dead, we have no idea. But if one person looks at it, the cat becomes either alive because the bottle may not topple over and kill the cat, or it might spill the bottle and kill the cat. Now, when we are not observing the cat, what is the state of the cat? Is it alive or is it dead? Quantum mechanical way of thinking about it is it's both. It's a superposition of both alive and dead. You don't know. You don't know the internal workings of Earth. And for example, I'll come to photon polarization, the quantum mechanical interpretation of that in a short way, because that is really the crux of the matter. So when you don't observe a system, you don't know what state it is in. But when you observe a system, there is a certain probability that it will either go into one state or the other. If I'm only talking about two-state system. And photon can have a polarization up or down, that is only a two-state system. So similarly, a cat can be either alive or dead, only a two-state system. So when you observe, the quantum mechanical system jumps into the state that you actually see. So if the cat is alive, it has moved into the state of being alive. If the cat is dead, it has moved into the state of being dead. It does it with a certain probability. That is all quantum mechanics can do, and nothing more than that. So now qubits are a direct consequence of the superposition. If you take a quantum object and have two quantum particles, for example, two electrons, the one electron at a given time, electron by the way has a spin half. So let's say, and spin half can be either plus half or minus half. So there is a two-state system. An electron, when you don't observe it, actually will be residing in both the states, in a superposition of the two states. And you can apply quantum mechanical operations on that so that the operations act in both the states simultaneously. So, whereas classically a bit can be either a 0 or a 1, quantum mechanically it's both. Now, if you have two objects, there are four possibilities. It can be up, 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 down, down, up, and down, down. So, as you increase the number of particles, the number of states that they can be in goes as q to the power n. And the quantum computer is constructed in such a way that all of these are parallelly getting affected by the operations you do. So in effect, it's massive parallelization. Parallelization exponentially done 2 to the power n. That is what qubits are used for, and that is how quantum computing is thought of. But in reality today, in the lab, there have been experiments where I think 3 quantum bits, 3 qubits have been put together in a control device. Entanglement is another interesting property which today we will not see, but is actually something that is relevant for quantum cryptography. But the mechanism that we are going to see may not involve entanglement. Entanglement is the following. Say there is a photon that emits an electron and a positron. Now the two of them fly apart. They go far away. Now as you know, electron and positron both can have two states, either a spin half or minus half. At any given time, you do not know which state it is. Now, if you measure it, it jumps into that state. But you also know that having had the common origin, there is conservation of angular momentum. Angular momentum is conserved. So, if I flip this, the other one has to flip, because that cannot be avoided. So, if you measure the spin of this electron, which let's say turns out to be half, and the original photon, let's say, was without or was as polarized up, which means let's say the spin was up. The two electron and the positron would both be pointing up. So if you measure this, the other electron, however far away it is, like maybe a few galaxies away, it still responds and immediately jumps into that state. So this was a contradiction in quantum mechanics that bothered Einstein, that bothered Niels Bohr, and it has been shown beyond a doubt that it does that. The other property that is important for us, which is purely quantum mechanical, is something called no cloning. You cannot clone a quantum state. If an object is in a quantum state, which is a superposition state, you cannot make a copy of that for the simple reason that if you make a copy, what happens, as I said in the beginning, if you observe a quantum mechanical system, what you observe is the state to which the quantum object goes to. Now, can you beat that by making a clone? And don't observe this quantum mechanical system, observe the clone. Because the clone has exact same properties as that, the same state and so on. So if you observe this, it shouldn't impact that. So if you observe the state of this, can you infer anything about the original quantum system? The answer is no. This is a protection that quantum mechanics builds itself by saying it's not possible to clone a quantum system. These are some of the properties that you may not see the direct relation, but are used in quantum cryptography. So how does photon polarization work? This is the crux of the matter in quantum mechanics. Now, as I said, the photon is nothing but a ray of light. Now, a ray of light consists of billions and billions of photons. What happens if you keep reducing the intensity of the light so that every time a photon hits the polarizing filter, only one photon hits? So you keep observing the photon as they get transmitted, but slowly one by one, and every time only one photon is transmitted through this thing. Classically, we saw that the intensity reduces if you transmit a bunch of photons together. The intensity of what you observe is going to be less than the original intensity. Now, what happens here if you send only one photon at a time? Since the photon is going to be transmitted if the polarization is parallel to the polarizer's axis, only those photons will pass through. And if the polarization is perpendicular or at any other angle which is not parallel to the polarizing filter, it's going to be blocked. Now, how then will you reconcile the fact that after collecting a large number of these single photons on the other side, you actually see a reduction in the intensity? This is the classic quantum mechanical way to use work. What happens is the photon that comes and hits the polarizer is never going to be in a state that either parallel to the axis of the polarizer or at an angle to the polarizer. It's going to be in both. It's going to be in a superposition of all the states, and the transmission happens so that the probability of any given single photon passing through the polarizer is actually proportional to cos alpha. So what classically we saw gets reproduced in quantum mechanics as well, and you will see that a single photon, even though you would assume, I mean, there's a similar thing. You can do the experiment not just with photon, with an electron. You have a screen and two, let's say, small holes. Classically, here is how we can visualize it. Supposing I have a screen and a hole and I have a gun in my hand. I'm a very good shot and I shoot. Either the bullet goes through one hole or the other hole. Now there is small probability that the bullets don't go through. Now if you look at how things happen at the other end of the screen, where the shots or the bullets are gone through, there is going to be a peak. The number of bullets that you observe on that side is right. And similarly on the other hole, there is going to be a peak. And so you will have a double peak. That's what you would observe. Quantum mechanically, what happens is, if instead of bullets you start shooting single electrons through these holes, each electron can either go through this hole or the other hole, and instead of seeing this double peak, what you will see is a diffraction pattern. You will see alternate peaks and troughs. So that is precisely the property that we will be using in this. So quantum mechanically we represent the photon as a superposition of the two states, and what goes through is actually proportional to the square of the amplitude, and that comes out to be cosine squared alpha. What do we do in quantum cryptography? Quantum cryptography actually is used only to share a secret. How is it done? It's again, we're going to use photons. Photons are going to be our key listening, and I'll show in detail how it is done. So initially you assume that the two parties don't have anything that they have shared. And by the way, I can tell you that this has been done in reality, and in last almost the reason why photon does. Photon is something that we technologically actually already use. Many of our communications happen on optical fibers. Optical fibers use light to transmit information. Many of our digital networks are optical fiber digital networks. So that is already one advantage. Second biggest advantage is it is in fact possible to exploit the quantum mechanical nature of light because it's easy to deal with them. Lasers are there which have monochromatic lights, very well focused, and some of these things require point-to-point communication. Line of sight is important, and that is possible using optical fiber channels. And this is the reason why photon is the natural charge. When we are doing quantum cryptography, we are using photons to transmit the key. How is the key done? Remember we said that photon can have two states of polarization. That is, it can be either up or down. If I'm assuming that, let's say, light is traveling like this, and the photon actually is vertically polarized, that means it's either vibrating up or down. So these are the two possible states. It can be either vertical or it can be horizontal. These are the two states, let's say, of the photon. Now, if we can assign the polarization state of the photon, because it's a two-state polarization, we can assign 0 and 1 to it. When we do that, if on the other end, the recipient's end, the polarization can be measured, you then have a string of zeros and ones. After all, what is a key? When you transmit a key, it's a bunch of zeros and ones. So when you have a reliable stream of zeros and ones, you have a shared secret. That is precisely what we are going to be doing. Other advantage in using photons, the quantum mechanical properties makes it possible that if somebody is trying to intervene in the middle, remember that I said I can intervene and say here 1,000 rupees is actually 10,000 rupees. If somebody actually messes up and is altering or is measuring the transmitted photons, you will get to know. And this way you can guarantee that nobody has actually messed with the photons that you use for the key. And the third advantage also is photons are plentiful in number. You can produce millions and millions of photons. So remember I said there is a theorem that says that a message transmitted is guaranteed to be 100% successful, that is 100% secure, if the length of the key is the same as the length of the message. Now for you to transmit a key that is as long as you want is quite easy. Whereas in the case of using a public key mechanism to use to transmit a long key would have cost you a lot. So these are some of the advantages that make photon the natural choice for doing quantum cryptography. So let's just quickly go through how this is done. Now, there are two possible polarization directions that can be chosen. One is vertical and horizontal, and the other is called a conjugate to this. If you take the plane that is 45 degrees to vertical, that is going to transmit the photons with a probability of exactly half. Now, what that does is it effectively randomizes the whole thing. So you end up getting no information from such systems. Such polarizations or bases for polarizations are called conjugate bases. So here, let me first just describe how this happens, and then we will see why it works. Usually in cryptography, Alice and Bob are the popular names that are used. Alice is the person who is sending the information, and Bob is the person who is receiving the information. And the person who is trying to steal the information is usually referred to as Eve. And we will see why Eve won't succeed. So, Alice chooses randomly a sequence of bases, either horizontal base or the diagonal base. This is a completely random choice. She sends a stream of bits. Now in the diagonal base, she sends a 0. In the vertical base, vertical horizontal base, she sends a 0. And let's say a 0 here is 45 degrees to the horizontal is 1 and 135 degrees to the horizontal is a 0. But it's just convention. Similarly, in the case of vertical horizontal, vertical is a 1 and horizontal is a 0 as the convention. So she chooses first to send a photon in the diagonal base, which is polarized 135 degrees. That's a 0. So in that base she transmits a 0. In the vertical horizontal base she transmits a 1, and so on. A randomly chosen one. And Bob at the other end, the recipient end, again randomly chooses some basis to measure the polarization. Now this choice and this choice are completely different. They don't know who has chosen what. Now Bob measures the photons received by him, the polarization effect, and just records it. After all the transmission is done, Alice and Bob communicate with each other classically and share the information about, Alice would share the information about the bases she has set it in, and Bob would then decide which of the bases were correct ones. That is, for example, this base was correctly chosen, this was a wrong one, this was a wrong one, this was correct, this was correct, wrong, correct, and so on. So he then decides that these were the correct bases that both Alice used and Bob measured the received photons. And the photon polarizations that were measured in the correct bases have to match. So if a 0 was sent, a 0 would be received here. A 1 was sent, a 0 was sent, but a 1 was received here. And 1 was sent and a 1 was received here. So on. So there are reasons sometimes when they do not match. This could be either transmission error. During the transmission something has happened and that information is lost, and the photon that is measured has a wrong polarization. Or there is Eve sitting there capturing these photons and messing with them. That is, Eve is capturing the photons, measuring them, and then retransmitting the photons, for example. So she is messing up with the photons, and hence what is received might not be the right one. Now the last possibility is I have written it wrong, which is likely what has happened. You find it here. I didn't intend to write it wrong. So now what do they do? Knowing that there is a set of correct bases that the two of them match, that the receiver and the sender have used the right base, they have received a bunch of photons. Now they know which ones, these are the ones that ought to be the correct ones. what Bob does is share the information, randomly chooses a few photons and says these were the polarizations I measured, but these are ones you sent. So a few photons randomly chosen, they would decide whether that is matching or not matching. If it is matching, then everything is fine. If it is not matching, then they know that there is some problem in the middle. Somebody has messed up. Assumption is somebody has messed up. So they drop this thing and then repeat the whole exercise. Now because it's photons, it's easy to repeat the exercise. So finally they are left with a bunch of photons which are the right ones, which everything matches, and only Bob and Alice know about these photons, the polarization state of these photons. Whereas I have shown only 4 of these. In practice, it can be 4 million, 4 billion, whatever you want. These being photons, there is no limit. So, what we have ended up achieving is that Alice and Bob, who started with no knowledge of each other, have now successfully shared a stream of photons which represents a bunch of zeros and ones, which is now the shared secret between them. Using this shared secret, now they can do any secret communication, any confidential information can be transmitted. There are various other applications such as authentication. I won't go into all of those, but suffice it to say that they are now able to share a secret without any problems. Of course, what are the kind of things that happens? On an average, only 50% of the photons will match the basis. And this is average. And statistically, you would expect that. And there will be further degradation due to transmission errors or eavesdropping, etc. So, in the end, they have agreed on a key which can now help them transmit information. Now, looking at the clock, it's 7:13, and also the battery in this is flashing. Everything is providentially coming together. So, what we've done is achieved a way of exchanging keys that would help two people communicate perfectly without any person intervening, and any confidential information can be exchanged this way. Classically, the result was dependent on the difficulty of solving a problem, but quantum mechanically it's first principles. The laws of quantum mechanics guarantee that this exchange of keys is perfectly secure. And since the length of the key that you can use is unlimited, you can choose the length of the key to be the length of the message itself, which then enables you to use mathematically proven theorems that give you perfect confidentiality. So, as I said at the beginning, I know that none of the beauty of the mathematics that goes into it came through. That unfortunately wasn't something I could communicate or convey to you without writing equations. And it's not just equations. Mathematics is not equations. Beautiful concepts require a lot of thinking. And if I have succeeded in exciting some of you to want to explore more, that I think would be a success. And thank you very much for listening.
They have covered quite a lot of quantum mechanics itself, whether it's Heisenberg or any other thing. But one question I have is, the processes used here are only polarization. Even though internally anything can be quantum mechanical behavior is there, actual process they are using, there is a polarizer from Alice and there is a filter at Bob. We have tried to exchange later on also, as you said, what was correct or what was wrong or something like that, so that you finally know the key. So why do we call it quantum when we actually do the process? If you take the equipment, all the equipment that you are using are only either a polarizer or a filter.
Right.
This is a doubt I have.
Right. The important thing to note is that even though you're using a polarizer, you're not using it classically. Classically, there will be a burst of photons. What we are interested in is capturing one photon at a time. When you deal with one photon at a time, it is quantum mechanics that dominate. It has to be quantum mechanics because classically, if you try to look at a system of single photon, classically it will either pass through or not pass through. Whereas quantum mechanically it has a probability of passing through even if it is in the wrong polarization. I mean, there is no wrong polarization. It's in a superposition state. So it is that property that is essential for this to work. It's the single photons, the level at which you send it as single photons, because we need zeros and ones. If you have a burst of photons as in a classical experiment, you will not be able to do it. That is the reason why it's quantum cryptography.
Sir, how this observer affects the observed, is there any mechanism in it? The observer may be a conscious being, awareness being. If he observes the observed, that is also having a consciousness, awareness, something like that? Why it is changing its movement? What is that mechanism involved in that?
Well, system, and you can't observe the universe without an observer. There is an observer, and the observer will see what the observer sees. If you're seeing something, there is reality to it. You cannot deny that I'm seeing an electron if you see an electron. But what you see is what you see. However, the only way to describe that we know internally is that it's in a state that nobody knows before you observed it, what it was. When you observed it, it is in the state that you observed it. And that transition is what is meant by saying it actually becomes what you observe. So it's a matter of describing the reality in nature and nothing, and really not very philosophical. However, a lot of philosophical questions do arise from it.
Anyone else? You are saying, in the transmission itself there can be errors also,
right,
in the optical fiber. And also due to Raman scattering also something can happen, the frequency can change, and those things also can mislead the result at the end of bob.
Yes, it will, anything that doesn't, we don't even go into the reason why it is. Assumption is that if something doesn't match, it can be due to eavesdropper, it can be due to transmission errors, it can be due to any other effect. It doesn't matter. As long as you are only speaking to the bits that match in the end, then everything will be fine.
Okay. Oh. No.